Fusion is the end game for energy, which means fusion is the way that the universe creates energy. So at some point in technological progress, kind of meeting how energy is created in the universe itself is the end game for technological progress. We will hit that goal. And frankly, we have hit that goal and we hit it 2 years ago. It's tremendously exciting. And so the commercialization of that technology is now, to my view, an inevitability.
Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hello and welcome to Hardware to Save a Planet. Today I'm joined by Scott Mercer, the CEO of Focused Energy, where he and his team are working on nuclear fusion for energy generation. They were founded in 2021 and have already raised over $175 million. I'm personally really interested in fusion, of course, because of the potential for virtually limitless, clean, and safe energy, but also because the engineering is super cool. Focused Energy's approach is a laser-driven fusion process, similar to what Lawrence Livermore National Labs used in 2022 when they achieved ignition, which means their experiment yielded more energy than was put into it. Scott tells me that choosing this architecture is important because it means they get to worry now about engineering risk instead of science risk. So their path to commercialization could be more predictable than approaches that haven't been proven in a lab yet. Scott joined Focus Energy as CEO after founding and leading Volta, an EV charging company that sold to Shell in 2023. Scott, it's great to have you. Thanks a lot for joining.
Absolutely. Thank you, Dylan. Appreciate you having me on.
So I got to ask, I always look at people's LinkedIn profile before we do these things, and I found yours pretty interesting. It suggests that your first job was CEO and founder of Volta, and you did that for 12 years before selling it to Shell. Is that the reality?
Somewhat the reality, yes. So I started Volta really right out of college and built the company from scratch through IPO. The company went public in August of 2021, which is the same month that NIF got ignition. I left the company after about 13 years, and then the subsequent team sold the company to Shell. So I think the sell the electric car charging company to Shell part was not my decision. Other than that, yes.
Okay. Pretty cool, though.
Thank you.
The only two roles on your resume are CEO of clean tech companies. Not bad.
I like building kind of big, complex infrastructure projects. So, and fusion is probably the biggest one I can imagine.
Yeah. So I was going to ask about that, actually. What is the link between what you were doing at Volta and Focused Energy, and how did you decide to make that switch?
I think that for the entirety of my working career, my interest has really been in just this idea that we are at this stage where technologically we have the opportunity to decouple energy production from resource consumption, right? To build an energy system that's truly generative, that's truly kind of able to scale with abundance, and that really solves so many of kind of the problems and the stories that we hear today. So for me, that was really thinking about what does it take to get there? At the outset, I think the earliest thing that was clear was to connect the energy system for the grid to the energy system for transportation and really move towards clean transportation. But the end game has always been, for me, fusion. And with the NIF ignition shot that happened in California in August of 2021, I thought that was the moment that fusion could truly move into the commercialization sphere.
Say more about that. So NIF is what, National Ignition Facility, something like that?
Yeah, so NIF is the National Ignition Facility at Lawrence Livermore. So it's one of the United States national research labs focusing on fusion programs. So we have fusion programs going on at a number of the national science labs in the United States. And the Lawrence Livermore program is somewhat unique in that it hosts this ignition facility, the National Ignition Facility, which is about a $5 billion laser facility used to concentrate laser energy on deuterium-tritium fuel pellets, to compress them from about a 4 millimeter sphere to about the diameter of a human hair and create controlled fusion. So lots of different approaches that have been posited to get controlled nuclear fusion. And the National Mission Facility was the first one to ever do it.
Why was that moment so pivotal?
So I think the fusion is a very, very technically challenging project. We have worked on many different approaches to get to controlled fusion and to controlled fusion that would be suitable for commercial energy generation. We've been working on it really since the 1950s, with the two major programs being laser fusion and magnetic fusion. I think that most people think about magnetic fusion, which is kind of the ITER project, which is this international cooperative project that has now been delayed until the mid to late 2030s. And I think that really what was exciting for me is that fusion has always had that sort of joke of being 20 years away and always will be. At the point that you actually saw the ignition shot at NIF, you realized that for laser fusion, we'd actually gotten over that hurdle. We actually had now true proof. We had actual scientific gain, proven, repeatable in a facility where we could actually continue to make improved progress. And that is a milestone that moves you into the realm of really a focus on engineering and commercialization rather than continuing to chase this elusive idea of energy gain out of fusion.
No longer a theory. It's happened.
Exactly. We've figured out the ingredients to do it and to do it repeatedly.
And let's take a minute and just explain fusion. And I'll pretend like this is for the listeners, but actually I feel like every time I learn this, I learn something new. So yeah, how would you explain what's actually happening in this fusion process?
Yeah. So I think in sort of thinking about how this all works, in the periodic table, generally atoms seek stability. And the most stable atom in the periodic table is iron. So Fe, kind of in the middle of the table. And I think in its most simple thoughtfulness here, the atoms at the lowest end of the periodic table and the atoms at the highest end of the periodic table tend to be those that are the easiest to use for energy generation. In the large atoms like uranium and plutonium, you have fission. Splitting them apart creates more stability as they get closer to kind of that iron, closer to the center of the table, and creates energy output as you split them apart. On the smaller end of the table, combining small atoms together creates more stability and thus creates energy output. So what we use is heavy hydrogen. So one proton, we use deuterium, one proton and one neutron, and tritium, one proton and two neutrons. Combining those together, you get helium and a neutron that shoots off from the reaction. And what you end up with is a helium atom that is just slightly less massive than the proton and neutron pairs from the reaction. What's happening actually in that reaction is some of that mass actually converts into energy in the classical E = mc squared reaction from Einstein. So you can think about a very small loss of mass, but that mass is converted into energy with the multiplier that is the speed of light squared, which is about 100 million billion. Again, very approximate. So you take a very tiny amount of mass times 100 million billion, that's the amount of energy you get out of a reaction like this. And so practically from an energy generation perspective, what this means is that we're combining deuterium, which is found in seawater, and tritium, which the reaction actually self-creates out of lithium in very small quantities to create massive amounts of energy in a very clean, controllable, safe way.
Yeah, and this was a helpful actually, that was a great explanation, by the way. Thank you. I appreciate this sort of periodic table visual. And this has been a helpful thing for me to realize. When I kind of first learned about fusion, it sounded like this magical thing where like creating energy out of nothing. But actually, and tell me if I have this wrong, it's analogous to burning a fuel in the sense that you are using fuel, the mass is converting to energy in the same way that fuel converts to heat when we burn a fuel. It's just that the energy density is so insanely much higher than in other fuels we have. And then there's no emissions and the fuel itself is really abundant.
We call it a burning reaction. It is a fuel, and your output is a massive amount of heat, neutrons, and then helium. And so at the point that you create this fusion reaction, for us, what we're using is a little 4 millimeter sphere of a combination of deuterium and tritium. You compress that sphere from 4 millimeters to about the diameter of a human hair using laser energy. When it compresses to about that size, you are at the conditions that are right for fusion. The atoms fuse into helium. Not all of them do. Right now at NIF, it's about 4 or 5% on the shots that they're showing today. From an energy generation perspective, you can get up to, let's say, about 30%, sort of broad brush. That creates, at that point, the hottest point in the solar system, approximately 150 million degrees. It radiates that energy out through the target chamber that we use to concentrate the laser energy. By the time it hits the walls of the target chamber, it's about 850 degrees, which is very similar temperatures to what you use for nuclear fission, for example. And we convert that heat energy into steam. The steam turns a turbine, and the turbine creates electricity.
Okay, so you're still generating heat, you're burning a fuel, essentially. It's just that energy density.
Yep. So we burn the fuel, we convert that into heat, convert the heat into steam, and sort of it starts to look very much like a classical power plant from there.
And as I understand it, this experiment at NIF showed net gain, but that's for the reaction itself. If you kind of take into account the full balance of plant, they're actually using a lot more energy than they're outputting through the reaction. Is that right?
Yeah. So I think this is one of the things that I find kind of fascinating about the NIF story as it's gone out into the public sphere is NIF was always designed to be a research facility. So it's designed to do single shot experiments that really in the configuration that it's in today are designed to replace underground atomic weapons testing. Meaning that what NIF is looking to simulate is the conditions that happen in a fusion bomb where the reaction was started by nuclear fission. When that happens, you take a nuclear fission reaction that creates X-rays. Those X-rays actually create inertial fusion, which is the same as what we're doing with direct laser energy. Those X-rays and inertially fuse the hydrogen in a fusion bomb. And NIF is owned by the NNSA, the National Nuclear Stockpile, in order to replace the underground weapons testing that we did back earlier in the 20th century. So the facility was never really designed in its current configuration for energy generation. It does have the capacity to be reconfigured for energy generation research. And we do have in the DOE National Labs programs other facilities that are more focused on energy generation. But there are a couple of very key changes that need to be made to the configuration and the architecture to take it from that kind of weapons lab into the commercial energy sphere. So kind of swords into plowshares, I think.
Which is where focused energy comes in, I imagine.
And that's kind of the next stage. That's where we come in. So we've been really looking at what are the ingredients that it takes to go from controlled, repeatable scientific proof into something that is fully tailored to a mission that is commercial energy generation as baseload power that would sit under the rest of the grid, instead of really using these from either just a pure research perspective or from really a weapons research perspective, which has been the historical use case for the shots done on NIF today.
Can you break that down? What are the big changes that need to happen?
So there's two big changes, broadly speaking, that we're looking at. And actually, really, I should call it three. The first is NIF was designed for single-shot research operations back in the 80s and 90s. It was designed frozen in 1993. It uses these very large high-energy lasers that are designed to charge and fire single shots at targets that are designed bespoke over a period of weeks or months for each shot. So that means that those lasers are quite old, and they were never really designed for energy efficiency. So the lasers themselves are about 0.5% energy efficient. If you want to build a power plant, you need the energy that the system feeds into the scientific reaction to not be a significant portion of the energy coming out of the facility. And so the lasers that we need to engineer for our facilities are 10 to 15% energy efficient. So 20 to 30 times the energy efficiency of what's happening in NIF. That's one of the first big key ingredients. That's enough.
That's enough of an efficiency gain. Okay.
And the nice thing about that side of the story, those lasers, that technology with that energy efficiency exists today. We have lasers in industrial use cases and defense use cases with far higher energy efficiency today with full solid state diode pump lasers than what we would need to move into a commercial energy regime. So that's the first major program. The second is redesigning the targets themselves and the architecture of the system for pure energy production and for rapid rate energy production rather than single shot weapon simulation. So NIF uses what's called a whole rum, which is a chamber that holds that little 4 millimeter pellet of deuterium-tritium fuel. The whole rum is used to essentially you bounce the laser energy into the chamber at an angle. It hits the chamber and bounces out an X-ray beam. So the laser hits the chamber, which is made out of a high-Z metal like gold. When it hits the metal, it shoots off an X-ray. That X-ray is what compresses the target into fusion conditions. If you have no interest in simulating weapons, and we do not have any interest in the weapons program here at Focused Energy, you can derive that target directly, where you shoot the laser energy directly at the little sphere of deuterium-tritium fuel. And that is a much, much more energy efficient way to create fusion conditions. So by moving the lasers from these sort of analog 90s single shot scientific research lasers into modern solid state lasers, you get about 20 to 30 times the energy efficiency of NIF. And then by using direct drive targets, you get, again, about 30 times the energy efficient of current shots at NIF. So it's pretty exciting from my standpoint because the recipe here is very clear for how you get from the program that's been going on in a post-ignition regime for the past several years and really in an experimental regime since about 2009. Going from that into commercial energy generation capabilities really is predominantly about engineering rather than about kind of this scientific can it or can't it.
Right. It's a combination of changing the goals of the system and maybe newer technology when it comes to the lasers.
And of course, I think then there are many other components of the system. I don't want to downplay the difficulty of creating a fusion energy architecture, but we do, of course, have to run these facilities as 24/7 baseload power. So you can imagine going from kind of a single shot event into a constantly operating machine, where instead of having these single shots that are inserted into the machine, shot with the laser energy, then reset, redesigned, et cetera, to try new, different target architectures, we're designing single target architecture that can be injected into the machine at rapid rate and shot at rapid rate constantly.
We're literally talking about these 4 millimeter balls being sort of inserted into this chamber, shot with a laser, kind of at rapid rate. So some sort of like industrial automation managing these little spheres.
I think the best way to think about it is the world's most scientifically advanced, largest, most powerful, and cleanest single-cylinder internal combustion engine that you could imagine. So you have a fuel injector that drops a little 4 millimeter droplet or sphere of deuterium-tritium fuel. Once it hits the center, you use the laser energy to compress it. You use additional laser energy to spark it and ignite it. It explodes. That heat radiates out. You capture the energy of the shot and you reset it and you do it again. And you do it about 10 times per second, which is about the speed of like a gasoline car engine at idle speed.
But you're creating, instead of enough energy to move a car, you're generating enough energy to power a city or something?
Really, 3 Coca-Cola cans full of what is functionally material refined from seawater and natural lithium would power San Francisco for a day.
It's not intuitive to me that a laser would compress this sphere of fuel like we're talking about? I mean, we're talking about light, right?
Yep.
Help me understand that.
So inertial fusion is kind of, as in the title, about using the inertia of the fuel itself to bring those atoms close enough that they actually fuse at enough speed with enough velocity that they get into fusion conditions. So it's not the laser energy itself that creates that. What you can imagine is a DT target that we create it's a 4 millimeter sphere. The sphere itself is a polymer shell, a plastic shell that's filled with cryogenically frozen deuterium-tritium in a foam matrix to keep it stable. The shell is not just a shell, it's actually the fuel for the reaction. So what happens in the target chamber, that fuel capsule will drop down from really be shot in from the target injector. At the point that it hits the center of the chamber, the lasers are triggered. They hit the surface of the target and they ablate that plastic shell away. The ablation basically creates a spherical inward-facing rocket engine. And so the sort of burn-off of the plastic shell is like rocket fuel that in the equal and opposite reaction propels the DT fuel towards the center. Once it hits the center, it gets there with enough inertia that it creates fusion. So I think it's the spherical inward-facing rocket engine is really the way that this thing works.
That's the way to think about it. Okay. Are there videos of this stuff?
There are. I mean, and there are real shots. NIF has done some of these shots. It's quite interesting because this all happens in a sort of time scale that is billionths of a second. So it does happen very quickly. But we have concept videos, and then there are also some actual still images where you can see the thing happen kind of like shot for shot.
Cool. So you've chosen this laser-based architecture, and the others are a lot of the other sort of tokamak-based, or like the ITER you mentioned, are essentially doing the same thing, but using a magnetic force to do the compression or the fusion.
Broadly speaking, the commercial fusion landscape that's focused on energy generation can be broken up into magnetic confinement fusion, laser inertial fusion, and a number of other different sort of experimental approaches. The vast majority of the science, the publishing, the research dollars that have gone into fusion for energy generation have gone into laser fusion and magnetic fusion. Magnetic fusion has been always a science-only program. So it's always been kind of in the public eye, where laser fusion was always a defense program. So it's always been behind the fence. We have laser fusion programs in multiple countries worldwide. They just have existed as part of the weapons programs. So they have lots of dollars, lots of research, lots of science, but far less publicity. Then there's a whole span of other projects that people have tried, especially from a commercialization perspective, that tend to be people trying for either kind of a cheaper fusion device, a cheaper ramp to fusion for investors, or just a different approach that someone has thought up that they want to see maybe it would work. But generally, the pedigree is in tokamaks and stellarators for magnetic fusion, and then in optically driven laser fusion for inertial fusion like ours.
Where are you in the development process? How much of these, you kind of laid out those three big areas that need to change from what's been proven in the lab. How far down that path are you?
Yeah, I should actually back up a little bit and talk about the origin story of Focused just briefly. So Focused actually started out of a scientific research lab out of the University of Darmstadt. It's a university in a very science-focused town right outside of Frankfurt. Started by a professor there at the university, Marcus Roth. And he had a research lab at the university that was studying the interaction of lasers and particles to create plasmas. So really a research lab perfectly suited for creating fusion field targets. That was the foundational IP of the company. So the company started the month that NIF got ignition. Marcus and Tom Forner, who's the other co-founder of the company, wrote the foundational paper, and then went out to the scientific leadership team at NIF that had run the ignition program and run the laser fusion programs in the National Lab system, and hired the majority of the senior leadership team that ran the program at NIF. So long pedigree in the company to a company that is only 3 years old. And the company now has been really pushing on what I would say is a very different narrative than what I see from the rest of the fusion ecosystem. in that I think the classical fusion story is kind of build prototype components, build a very small scale first machine for proof of concept, build a larger machine to hone the concept, build perhaps a machine capable of seeing scientific gain, maybe engineering gain, et cetera, and sort of laddering up. For Focused, we're starting from a point of the big machine already exists. We've seen proof that this works scientifically. So we have a very different roadmap forward. Instead of having to kind of ramp up, find investor capital to build the still multi-billion-dollar prototype that would be required to prove laser inertial fusion, we're starting with the fact that actually exists, moving down into a smaller scale machine that shows all of the proof points that you need to show about the ability to inject targets at speed, to track them rapidly, to prototype these diode-pumped solid-state lasers, everything that an energy operator would need to say, okay, we know that there's proof of gain. We know that you can inject the targets, compress the targets, hit them with the lasers. You have lasers that are suitable. We're ready to actually begin the development process for a power plant. So that's kind of where we sit today, is we have been doing the component development and really had the company focus on the development of this smaller scale integrated testing facility, with the thought that once you have proof of scientific gain and then proof of all the core engineering concepts that need you to move from gain in a lab to commercial readiness, that you can start to have serious commercial deployment conversations really quite early, I would say, as compared to my expectation for the larger fusion landscape.
You have the luxury of not needing to prove the science with this massive investment focus on the engineering.
We as taxpayers have already shouldered the bill for proving scientific gain. So that makes it a little easier for the investor story to really say, you guys don't have to pay for this.
So these smaller scale systems won't be at a scale that will achieve gain?
In physics parlance, it's called a subscale facility because the actual physics scale in a linear fashion. So as long as you can prove that you can do the majority of these concepts at smaller energy scale, you know that when you add additional energy, you do get to ignition conditions, you get to gain conditions. And I think that a lot of this for me is about ascribing reasonable risk from an investor perspective and from a customer perspective. We won't be able to prove every single component of the operation of a first generation commercial fusion facility, but we don't think that we have to. Because if you have a scientifically proven concept, you have a commercially viable facility architecture. Really, if you look at the geopolitical landscape of energy, energy is geopolitics. And so at the point that you have this, the race does start. And the race starts quite aggressively in that the countries that master fusion energy will change their geopolitical standing. I think we are kind of right at this precipice where, given sufficient proof for laser fusion in the engineering capabilities, given magnetic fusion, which has been going down a very strong engineering pathway, now being able to prove its scientific pedigree, you have really now, I think, the very beginnings of a push towards a massive global energy shift in how energy works as kind of the foundation of global economics and the foundation of global geopolitics. So all that to say, the dollars at play are so big that as you can get to enough proof points to give people confidence, the shift in the market becomes very fast.
How close are you at Focus Energy to getting to that point?
We're already working with nuclear experienced energy operators to really start to look at, from a customer perspective, what else do people need to see? The way I would think about this, customers meaning, I would say, a first generation commercial fusion customer in an ideal case is probably a combination of a government and a nuclear experienced energy operator, or at least an experienced scaled energy operator. We're not making small systems. These are gigawatt sized baseload power systems. So one focused energy reactor would be about the size to power a mid-sized city, a city the size of San Francisco proper. And first of a kind hardware is likely to be commercially ready, but probably not commercially priced. Those first 10 or 15 power plants, like a lot of first generation energy generation facilities, will be probably a little bit more expensive on an LCOE basis, levelized cost of energy basis, than they will be as you start to get into the scaled production. So you're really looking for kind of a country to underwrite the risk, and you're looking for an operator to partner with to do the design, development, deployment. So Focus currently participates in the fusion commercialization programs in the US and in Germany. So the DOE has a public-private partnership program that has accepted 7 of 50 fusion companies thereabouts in the landscape. And then Germany has what they call their Fusion 2040 program, which is working with a smaller number of fusion companies towards fusion commercialization before 2040. So we're in both of those programs. I think the idea for us is that we expect to work with a handful of countries and country scale operators. We expect to really have conversations around selling this first generation, first of a kind power plants, and to work backwards from that first generation sort of, I would say, like supply chain architecture, the manufacturing architecture, backwards into kind of the development cycle for those first customer power plants from here. So all that to say, in a given facility, we need a large quantity of smaller and high energy lasers, and small being relative. These are still very complicated and $1 million plus individual laser modules, but we need to make those in a quantity of thousands per year. So how do you start to build a supply chain architecture for that? Where might that go? How would that contribute to a local economy? How do you actually even build the supplier architecture for a piece of hardware like this that has never been done, that is very complicated, very sophisticated, but needs to be built at large scale?
Sorry, why do you need thousands of lasers?
When we think about building these facilities, the easiest way to build these high energy lasers is to build manufacturable lasers that can be built on a supply chain. So the lasers that we need exist today. They're built kind of like satellites, built one at a time. NIF, as an example, they built all of the factories to build the glass for the lasers. They built the components for the lasers. The factories got built. They built all the glass for all the lasers at NIF. Then they got shut down. So they're built very bespoke as one-of-a-kind pieces of hardware. We're building the entirety of the industry. So we don't expect to build lasers for a single prototype facility. We expect to build a supply chain that is foundational to putting gigawatt scale power plants on the grid every few days.
Okay, you need thousands of lasers for thousands of generation
Correct.
facilities.
And even for a single facility, our pilot plant requires hundreds of individual laser modules to get up and running. A gigawatt scale power plant is a very large power plant. And what we do is bundle together about 2,000 kilojoule sized lasers into bundled arrays to provide the energy to the facility itself. So you could think about it almost as computers in a data center. You're racking these high energy lasers into bundles. You're sort of bundling them together. And then that energy combines in a single beamline into the target chamber to hit the target.
Cool. What about the supply chain for the fuel? Is this something we currently can produce in sufficient volume?
So our fuel has 2 components. One is the actual raw materials of the fuel, so deuterium and tritium. And then the second is the manufacturing and the precision manufacturing of the fuel targets themselves. We call them pearls. They're kind of these perfect spherical spheres. Yeah. They contain the polymer shell that then contain the foam matrix that holds in that DT fuel. So for the actual fuel itself, deuterium is 1 in every 7,000 or so molecules of seawater. So you actually can get it out of water. Tritium has a very short half-life, so it doesn't exist naturally. We have a very small quantity of tritium available to us at any given time. But the reaction in a fusion reactor shoots off neutrons that can be used to breed tritium in the reaction itself. So what we do is we shoot the neutrons out of the fusion reaction, pass through the first wall of the machine, that target chamber wall. They hit a blanket of lithium. And when the neutrons hit lithium, they create tritium.
So what, then you need to produce your pearls on the spot with that tritium?
We produce the pearls on site. So the pearls are a polymer shell that is cured, that is coated with a very thin coating of a high Z metal, and then filled with that deuterium-tritium fuel mix.
So your facility's not only shooting the targets and doing the fusion, but actually producing the pearls.
They produce
that contain the fuel
on site,
sort of on demand.
Because these are baseload power plants. They are really next generation baseload power plants. I think one of the biggest advantages to fusion as baseload power is the ability for it to be as independent as possible, right? Like you don't want the facility to cease operations because the trucks or the helicopter or whatever can't get fuel to the facility for the next month's operations. So the idea that as much of it is contained on site as possible, I think is one of the big appeals of the architecture.
Yeah, cool. What do you think is the biggest kind of technical hurdle to overcome still? What keeps you up at night?
We have kind of an internal risk register, which is the remaining things that we need to solve, the remaining things that we need to prove to get this deployed. I think that for me, there are still very strong kind of scientific engineering hurdles that we need to get over. They don't feel like the insurmountable parts of the system. Right now, the things that worry me are really the prosaic things. How do you manufacture enough glass fast enough? How do you manufacture the constituent components fast enough? How do you build these laser supply chains fast enough? And how do you do this all in a coordinated fashion that sets up what is currently about a 70% company to build an industry that is going to be worth tens of billions, if not hundreds of billions of dollars on an annual basis going forward. So that mismatch is, I think, the thing that keeps me from sleeping.
And then your business model will be what? Will you be selling energy?
We're kind of the technology developer. And so we're selling the development, design, and final architecture of the fusion power plant itself. And then we supply the pearls. So the fusion fuel IP is owned by Focused Energy. So we own the IP around these pearls. And so I think that creates a business model that's a little bit more tenable than going out to market and saying, hey, we want to be the operator of these facilities forever. We want to replace our current kind of utility system. I think that's not likely to happen. So we really want to be kind of like the design developer of a efficient power plant where we're taking an operating license, we're taking a development fee, and we're working with governments, we're working with operator customers, utility customers.
How has the recent administration change in the US affected you guys?
I think that I come out of the electric vehicle space, which I was always excited about because it was both something that had an environmental benefit, but also was very clearly an economic advantage. Frankly, fusion is far more bipartisan than a lot of other clean energy projects might be. So we've seen Chris Wright in the U.S. administration come out and say that the DOE has strong interest in fusion. They have interest in commercializing tech coming out of the national labs. Those have both been good. I think that fusion fits very well with any first world nation's future energy policy. I think our concern is really only around kind of this decline in globalization. So being a global company at heart in Focused and fusion being something that really will sell into global customers, I think that's really been the only major concern for us in our roadmap. We're not as worried as I might have been if I were still at Volta doing electric car things.
Fast forwarding into the future, when would you project that we're at a place where fusion is a meaningful mix of our energy landscape?
So I think this kind of dovetails back to that, what keeps me up at night question, is it really is about the scale of deployment, supply chain readiness, and the seriousness of investors, industrial partners, and government scale actors to invest early. This is such a big change, but it does building energy infrastructure of this scale and sophistication takes time and takes pre-planning. So I do think that the fusion industry's goals of having power on the grid, having first systems on the grid in the mid-2030s is quite realistic. I think that first commercial deployments in the late 2030s, starting to really roll into that is realistic. I think that scaled deployment really begins in the 2040s. And then I think it really is a scramble to build as fast as you absolutely can. That all is presaged by this idea that building power plant architectures is not easy. If you want to build systems that have enough energy production capacity to be relevant to the global energy system, they need to be big. If they're big, they usually take a long time to plan. So when we talk about having these facilities sort of deploying at scale in the 2040s, that means we have very clear visibility onto where those facilities are going in the early to mid 2030s.
Oh, wow.
So all this to say, I expect to have those first 20 power plants sold before the end of the decade. I expect to know where they're going, which means that Focus expects to have an order book that counts in the hundreds of billions of dollars for facilities before the decade's out. It doesn't mean that we will have those facilities up, on, and running. But from an investor perspective, it means that commercial story is a very compelling one, right? Like you go from here to saying, great, what does an energy operator need in a post-proven gain world to commit to the development of a power plant? And if you have one, you will have multiple. And we are really starting those conversations seriously and in earnest.
Well, and for that to really kick over into orders, you need to get to a place where you've kind of proven out these engineering risks and the kind of supply chain risks that you're talking about, or at least to a level enough to kind of get people on board.
Exactly. We have this engineering risk register. We're kind of trying to figure out how quickly you can burn those programs down. What can you test in the lab? What can you test at small scale? Then how do you get what is being developed by other third-party partners? And what level of confidence do you need to give someone in order for them to take the remaining amount of risk that's reasonable and rational? I mean, we are building what would be one of the most valuable industrial ecosystems in history and one of the most politically important industrial ecosystems in history. So at some point, people will take some risk. And I think we're right at that precipice in fusion of many projects that are still a little wild and speculative and never will see commercialization, and the start of some of the core scientific work turning into commercial projects that have a true commercial roadmap. So as that sorts itself out, you really do start to ramp into a very, very fast-moving ecosystem.
Maybe this is kind of a fuzzy question, but on the surface, when we talk about virtually limitless, clean, safe energy, very inexpensive, like with the fuel is abundant, it could last however many millennia. This feels like it would solve all of our problems, kind of, right? Like this just feels like a hack. Like it solves climate change, it solves like inequality. Is that the right way to think about this? Is this that big of a deal? Or when you kind of layer in the realities of like the scaling challenges and everything, it's always only going to be a part of the energy mix. It's sort of like getting a bunch more like hydropower on the grid, but we still have a lot of the same challenges we have today. How do you look at that future?
I think I always struggle with how to talk about that because I feel that it is so big that it almost loses meaning. Fusion is the end game for energy, which means fusion is the way that the universe creates energy. So at some point in technological progress, kind of meeting how energy is created in the universe itself is the end game for technological progress. We will hit that goal. And frankly, we have hit that goal and we hit it 2 years ago. It's tremendously exciting. And so the commercialization of that technology is now, to my view, an inevitability. The energy potential of the fuel means that it will be an economic reality, that fusion will be the most inexpensive fuel source available at some point. The question is really when. And really, from my standpoint, also on the counter side to this, I think that this is a requirement to the continued progress of civilization. You have to master the decoupling of energy generation from resource consumption for us to continue to progress, certainly economically as a civilization, to kind of go from the 8 billion plus people that we have today to a global population that will grow still until probably the end of the century, to continue to bring people up in material resources, to have the extra energy and resources that will be needed to mitigate all of these sort of climate issues that we've created that can be remediated through kind of having access to that additional energy. I think that fusion is really the long-term game for us. And I think that I'm excited to be in the space now because we're just at that point where it gets real enough that people start to take that seriously as part of a system.
I have 3 last questions I ask everybody. The first is, how optimistic or pessimistic are you about the future of the planet and why?
Certainly optimistic. I think that we will continue to develop the solutions that we need to develop. I think that we are certainly learning lessons now, but there are solutions to the problems that we've created. And I think we're well on our way.
Who's another company or individual doing something to address climate change that's inspiring you?
I think that although perhaps as an early stage startup, it's a bit of a shameless plug, but I think that the folks that are investing in technologies like this with very long time horizons for the collective good rather than kind of for the near-term economic benefits, I really do admire. I think people that are really pushing this forward in lieu of strong collective action to do programs that are long-term. So some of these earlier stage investors that think about this kind of almost as what you should do with money once you've gotten to a point where have the ability to actually drive forward change. I think I appreciate that. I think that we are in a little bit too near-term capitalism view right now where people want kind of returns now rather than thinking about these longer-term collective gains. So folks that think bigger and folks that think longer, I think are very important. And especially those that kind of can replace that collective action that, the US used to be very, very good at in kind of the Apollo era, et cetera. I think that's what I would love to kind of get back to.
Yeah, I'm glad you mentioned that. I meant to ask you about kind of how you've been successful raising funds with something that is on such a long time scale that doesn't really fit the sort of 10-year fund timeline.
So for us, the frank answer is it does. And it's been part of my role in the company in the last years, really thinking about how do you get the company to pragmatically deploy from here to scale in milestones that meet investor targets and in a way that does match the current capital environment. We know that money chases short-term goals. So how do you make sure that you can build value on timescales that people are comfortable with? Again, I think the conversations we're having with customers really put us on the pathway to sell those first power plants before the end of the decade. And to sell them not as power purchase agreements where it's like, hey, if you build it, then call me maybe. This is a serious commercial deployment contract with a government sponsor, with a nuclear experienced operator or an energy experienced operator, and with contracts that are valued in the tens of billions of dollars on a per contract basis. Doing that before the end of the decade, that's sort of 4 to 5 years to a business that has visibility into hundreds of billions of dollars in contracts. I think, investors would be happy with that story. So for me, it's really getting over the hurdle of that early perception that fusion is where you wheelbarrow in a bundle of money to a bunch of scientists to go into a lab and experiment with a machine for a decade or two to advance the science and see what happens. That's not where we are anymore. We're in a proven science regime where now it really is just about the engineering and commercialization of the system.
So it really fits that kind of typical VC model a lot better now.
It should. I think that, the rational path to capital returns here is the returns will be very, very large. The scale ambition of the company is very, very large. So it really is about making sure the company is ready to execute on that fast ramp rather than being concerned that you wouldn't see the return in a reasonable time frame. But a lot of that is just story education and getting people kind of up to speed. The market has changed for fusion in the last 2 years. The NNSA is really not a proponent of commercial energy generation from inertial fusion. So we have to really go out there and be the sort of the front line of that storytelling for the space.
What advice do you have for someone not working in climate today who wants to do something to help?
I think that so many things that are climate are a proxy for a reinvention of industry, a reinvention of technology, systems that generally are just economically better. So I would say that getting involved in climate is really about getting involved in these technologies that are foundational to growth. I think that it is realizing that there are career opportunities in something like this, in anything from construction and electrical and plumbing all the way up to going into high-end physics research background programs. So I would say kind of taking a first principles look at where the world heads economically, at where these systems will end up going, and then sort of thinking about what piece you want to work at. I think that there are many different opportunities. And the other thing I would say is don't be afraid to get your hands dirty. And I think there's a lot of value in building the things. And that is where a lot of the money flows as well.
Well, Scott, I love it. Thanks a lot for your time. I really appreciate it.
Absolutely. Dylan, thank you for having me on.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.